Hey there, everyone. I have one last problem for us in this energy chapter. We're given a potential energy function for a proton, this one here. And it's a special kind of function because it indicates that we're dealing with a conservative force. We need to use that to solve 6 different parts, A through F. There's a lot to do here, and I know this will end up being a longer video, so timestamps will be included below. Let's get started. Part A wants us to show that our potential energy function can be written into the form that was given earlier in the problem description. That form doesn't contain beta, so we'll need to start with the definition of x naught. I'm going to switch the places of beta and x naught, then grab our potential function so that we can plug in this definition for beta like this. Here's the result when you simplify that. Next, there's 2 steps of factoring that we need to do. The first round involves taking out alpha from both terms. The second requires factoring out a 1 over x naught squared. We don't have x naught squared in the denominators here, but we can still factor it out. That's okay. We just need to add the same thing in both numerators so that if we distribute 1 over x naught, we get the same thing back that we started with here in the middle step. The first term inside the square brackets can be rewritten as x naught over x raised to the second power. And in the second term, one factor of x naught in the numerator will cancel out with this one in the denominator. This matches the form from the problem description, so now we can move on to the other 3 requirements in part A. The first is graphing this function. We're not given any specific values for alpha, beta, or x naught, so I've set our variables equal to 1 so we can get the general form of the potential energy curve. Let's move on to the next task, which is calculating the potential energy at the point x naught. Here's our potential function again, with x naught substituted in for x. Inside the square brackets, both of our terms will end up reducing to 1, and 1 minus 1 is just 0. So the potential energy at the release point of x naught is 0. The last thing to do is to show on the graph where the point x naught is located. It's kind of a trick question. You may be tempted to go back to the plot and say, here it is, right here. It's at x is equal to 1. That is true, but it's only for a special case where all the constants are equal to 1. If you set alpha and beta to some other positive numbers, x naught could be located somewhere totally different. So we need a more general answer that can identify where x naught is regardless of what the constants are. And thankfully we can do that without having to calculate anything. Notice that this function only has a single x-intercept. If we look past it and increase the values of x, our function gets closer and closer to the x-axis, but it never touches it. This means no matter what positive finite values that you pick for alpha and beta, there will only be one spot where the potential energy is 0, because there will only ever be one x-intercept. And that is exactly where you'll find x naught. And it's the most general way of stating its location on the graph without using specific cases or test numbers. Now that we've covered all those possibilities, let's move on to part B. we need to use our potential function to get a velocity function for the proton, then graph that as well. Let's start by reviewing a special feature of the work done by conservative forces. Whenever you have a conservative force, the work it does is equal to the negative change in potential energy. So initial minus the final. In our situation, the proton is released from the point x0 and it ends up at some future value of x. So we can rewrite this difference with that in mind. Also, recall the definition of the work-energy theorem, which says that the net work that's done on an object is equal to the positive change in its kinetic energy. The final velocity will be the velocity found at some future x value, and the initial velocity is the one that we start with at x0. We're going to equate these two expressions to get the velocity as a function of x, but there's some things that we can reduce first. We calculated the potential energy at the point x0 back in part A, which was 0. So let's get rid of that term. Additionally, we released the proton from that point, and that language implies that it starts from rest. So the kinetic energy at x0 is 0 too. With those taken care of, we can now set these work expressions equal to each other down at the bottom, like this. We want the velocity as a function of x, so let's multiply both sides by 2, then divide both by m, and then take the square root. Now we have an expression for the velocity, but we're not quite done yet. We still have to plug in the potential energy function as well. And we'll need to pretty this up a bit by having all these factored out quantities together, which allows us to remove the unnecessary outer parentheses, like this. That negative sign here under the square root is also a little ugly, so I'm going to distribute that into the square brackets, which just rearranges those inner terms. And now we end up with a very nice looking velocity function. If we graph it, we can see there's some interesting behavior going on. The proton starts from rest at the x-intercept, which is x0, and then it quickly gains speed. It hits a maximum, and then it begins to slow down asymptotically, coming to a stop only when x becomes infinity. That's everything for part B. Part C wants us to use this velocity function to get two things: the value of x at which this maximum speed occurs, and the maximum speed itself at that point. To get the x value, we're going to take a derivative of this velocity function and set it equal to 0, and then solve for the value of x. This derivative will require the chain rule, because we're taking the derivative of one function nested inside of another. Let's grab the innermost function, which is everything here underneath the square root, and we'll set that equal to a substitution variable, which I'm calling u. We need a derivative of u with respect to x, so let's factor out all these coefficients and apply the derivative to everything here within the square brackets. Now it looks challenging, but if you change the expression to use exponent notation instead, it's pretty clear that we only need to apply the derivative power rule here. The x-naughts are just constants, and so the derivative doesn't care about those. When we apply that derivative, in the first term, The negative 1 will drop down to become the new coefficient, and we subtract 1 from negative 1 to get a new exponent of negative 2. It's the same idea with this second term. The negative 2 will get pulled down to become the coefficient, which will change this negative sign to positive, and we subtract 1 from negative 2 to get negative 3. Here's the result. We don't really need this expression in exponent form anymore, so I'm going to switch it back to fractional. Now we're ready to keep going. The chain rule says that we need to take a derivative of the outer function with respect to our substitution variable u and multiply that by the derivative of u with respect to x, which is what we just finished. Here's what we get. The derivative of the square root function gives us 1 divided by 2 times the square root of u, and we're multiplying that by everything that we got from before. The final step in this chain rule is converting from u back to x. So let's grab our u expression and plug that into the square root in the denominator. Now, this looks atrocious, but we're in luck. We're setting this whole thing equal to 0. So a good chunk of it is going to melt away. Let's multiply both sides by everything in this first denominator here on the left, which will just leave us with this. Now we can divide both sides by 2 alpha and multiply both sides by m times x naught squared, and that will kill the coefficient and allow us to drop the square brackets. The second term gets moved over to the other side, and we're going to solve for x again, just like we did in part A. Divide both sides by a single factor of x naught, and then multiply both sides by x cubed. Our result is that the maximum velocity occurs at an x value equal to 2 times whatever x naught is. Let's grab this and plug it into the velocity function. Inside the square brackets, the x naught terms will divide out, and we'll be taking 1/2 minus 1/4 there, which is 1/4. The 2 divided by 4 here can be simplified to 1/2. So the maximum velocity will be this expression here. Part C is all finished. To answer part D, we'll need another special characteristic of conservative forces, which says that the value of the force at any point is equal to the negative derivative of the potential energy function at any point. Since we want the value of the force at 2 times x naught, let's plug that in and see what we get. This is nice because it requires no work at all. Notice that we're taking an x derivative of a bunch of constants now. You know what that means? The result is 0. So at the x value of maximum velocity, the proton experiences no force. Part D is done. For part E, we're releasing the proton from a new location, which is 3 times alpha over beta. We already know that alpha over beta is what x naught is, so let's just call this 3 times x naught. Where would we find that on a graph? Well, it's going to be 3 times the value of whatever the x-intercept is, depending on the values of the constants. That's the most general way to put it. When we release the proton at this new point, it's going to affect the form of our velocity function. Let's go back to work done by the conservative force. In this new situation, the initial potential energy comes from the point 3 times x naught, and the final is, again, at some future location that has a x value of just x. The problem is, we don't know what the value of the potential energy is at 3 times x naught. We're going to have to figure that out before continuing. Thankfully, it's just a couple steps. First, grab the potential function and insert 3 times x naught everywhere we had x. The inner x naughts will cancel out like we're used to, and you'll end up getting 1/9 minus 1/3 inside the square brackets, which reduces to -2/9. Those square brackets aren't needed anymore, so let's just combine the whole thing and stick that up top for now. The work-energy theorem still applies, and like in the earlier parts, we're releasing this proton from rest, so the second term still goes to 0. Let's combine these two expressions down below once again. We want the velocity as a function of x, so same steps as last time. Multiply both sides by 2, divide both by m, and then take the square root. Go ahead and insert the potential function, and you'll have a little cleanup to do. Alpha over x naught squared can be taken outside these outermost parentheses, and we can also distribute this second negative sign into the square brackets and rewrite the whole thing like this. That's our velocity function for the new release point. Let's add it to the graph and see how it looks. Quite different from that green velocity function, isn't it? Let's get a sense of how to interpret this. It helps if you picture the proton like a marble rolling down a half pipe or something. It starts with a velocity of 0 at 3 times x naught, and it gets pushed towards lower potential energy by the conservative force, which will make it move to the left. It gains speed as potential energy is converted to kinetic, and it hits a maximum speed at roughly the same location as before. Then it will slow down back to 0 as all the kinetic energy gets converted back to potential. Once it reaches this side, the conservative force acting on it still wants to push it to smaller values of potential energy, which is now on the right. So it'll start rolling again, but this time in the opposite direction. Once it returns back to 3 times x naught, the lower potential values are once again on the left, so this proton will forever oscillate back and forth between these two spots when we release it from 3 times x naught. That's everything for part E. The final task in part F is to find the minimum and maximum values of x for our two release points. For the first release point, we actually covered those already back in part B. The minimum x value is the release point of x naught, and the proton slows to 0 once x approaches infinity. So there's really nothing more to add on that. At the second point, we'll need to set this new velocity function equal to 0 and see what we get. Go ahead and square both sides and get rid of the coefficients that are attached to the outer parentheses. You'll also want to move this -2/9 over to the right-hand side to make it positive. We'll need a common denominator on the left, so let's multiply this first term by x over x. Now, both terms have x squared downstairs, which allows us to bring them together like this. if we first cross multiply and then distribute the 9 and move everything over to the right-hand side, we get a result that has the same form of a quadratic expression. And thankfully, we can factor it like 1, and we don't need to use the quadratic formula. If we set the first factored term to 0 and move the negative term over to the other side, then divide both sides by 2, we get the minimum x value of 1.5 times x naught. Setting this second factored chunk to 0 gives us our release point of 3 times x naught. So there is our minimum and maximum x values for the second release point. Part F is done, and we are finally finished. Here's some review on the solution card in case you may have skipped through some parts. In Part A, we did a bunch of algebra to match the potential energy expression that the problem wanted, and we found that at the release point of x naught, the potential energy will be 0. That release point is found wherever the x-intercept is located, which depends on the values of alpha and beta. In Part B, we used the work done by the conservative force in addition to the work-energy theorem to solve for the velocity function, which is this expression here. When we plotted it, we saw that the proton starts from rest at the x-intercept, it speeds up to a maximum, and then it asymptotically slows down to 0 at x is equal to infinity. To find that maximum, we took a derivative of this velocity function in Part C, and we set it equal to 0, which required use of the chain rule. When that was complete, we saw that the maximum speed of the proton occurred at the x value of 2 times x naught. And when you plug that x value into the velocity function, you get the following expression, which represents the maximum speed. For Part D, we used a special quality of conservative forces to find the value of the force at the point 2 times x naught, which was the negative derivative of a bunch of constants, resulting in 0. Part E had us release the proton from a new point, x1, which was just 3 times the value of the x-intercept. And after doing all the work from Part B all over again, we saw that the velocity function changed into something a little bit different. For Part F, we talked about how the initial release point at x naught was the minimum x value for the proton, and the maximum is at infinity, where it slows to 0. And for the second release point, we set the new velocity function from Part E equal to 0, and we factored the result, which gave us the following minimum and maximum x values. And all of that agreed with what we saw on the graphs. We can now bring the energy chapter to a close. If you've sat through this whole video, you deserve a medal. Thank you all for your time and your patience, and I'll have some new videos out soon covering our next topic, momentum and impulse. See you then.